Today's lesson, section 6.1, we're going to split this into two parts. Let's call this A, exponential growth and decay. So the first thing I want you to study is this first core concept. And what we're looking at is the graph of an exponential growth function. And the key to this would be looking at part of this equation. Here's the equation right here. And the most important part of this is noting, well, a couple things. The exponent is a variable, which makes this an exponential equation. But b is the base number, and if it's greater than 1, then it's going to be an exponential growth function. So you can see the picture of this graph rises. And another interesting fact about this is the graph has what's called an asymptote, which is actually the x-axis right here. And the graph will approach the x-axis, but never cross it. And the best way to understand that is to create a table of values and experiment. One last thing I want to note here. The domain of this function is all real numbers, as you can see, and the range is everything above 0, but not including it. Now, let's go ahead and take a look at the converse of this, which is a decay function. So here's the equation again, but the difference is the value of b will be in between 0 and 1. Now, you may wonder what's going on there. It can't be negative, and b cannot be 1, because if it were 1, then you would have a function of 1 being raised to any exponent, which is the value of 1. It would be a constant straight line. Domain is still all real numbers, but the range, and the range is still all values greater than 0. It has an asymptote, like we saw in the other picture. So now you got an idea of what these functions look like. Let's go ahead and look at some applications of this formula. So now here's the growth and decay formula for an exponential function. And this is the same thing as the equation we just saw. B would be the same thing as 1 plus or minus r. All right, let's define what everything means here. So first of all, y. Okay, that is the answer that you're looking for. Okay, so that's the total, or your answer. Yeah, that's bad. Let's just leave it at total. A, that's your starting value in your situation. Okay? Now I'm going to highlight this. This represents the growth or decay amount. Okay? So growth is if this value is larger than 1. Decay is if this value is in between. I made a mistake there, sorry. Well, I guess I could go with that. As if this value is in between 0 to 1. Let's put it that way. Just like you saw with the decay graph. And then the last part is T is your number of growth or decay periods. How many times does this event grow or decay? All right, now let's put this formula into use. Can we tell whether or not these equations represent growth or decay. Well, in part A, I would say that we could write this formula like this. I would say that A is 1, growth rate is 2, and then my exponent is x. Now this right here is a number that's bigger than 1, so that's got to be growth. Now I've taken the time to graph these on Desmos, so let's look. Okay, here's our first graph, and you can see how it grows. Definitely exponential growth. Let's go on to part B. What do you think about that? Well, if I rewrite this, I'll do this for a couple more. There's an understood 1 here. Growth rate is 1/2. Then you have x. So let's take a look at that 1/2. That's between 0 and 1. This is decay. And if we take a look at that on Desmos, I've got it programmed in here. Look at that. And you can see how it's going downhill from left to right. Let's go to the next one. Okay. Why don't you everybody give those a try and tell me if they're growth or decay. All right. So in number 1, because this 4 is larger than 1, this would be growth. And we could look at a picture of this on Desmos. There it is. You can see it's growth. That value of B, or the parentheses 1 plus or minus R, is bigger than 1. That's growth. Number 2, looking at this 2/3. 2/3 is less than 1. This will be decay. Well, we could take a look at that on Desmos as well. So now you're getting an idea of what these graphs look like for exponential growth or decay. Number 3, 0.25 is definitely less than 1, right? So it'll be a decay graph. Let's take a look on Desmos. Decay once again. 1.5 is bigger than 1. This will be exponential growth. So we can kind of predict what this graph might look like. And there you go. So I hope that helps you visualize what these exponential functions may look like. Let's move on. Let's see if we can answer a question like this. So the value of a car is Y, and it's in thousands of dollars. It can be approximated by this model equation, which is an exponential equation. T is a number of years since the car was new. So what we want to do is tell whether that model represents exponential growth or exponential decay, first of all. So when we're looking at this, the value we should look at for part A is this 0.85. That is less than 1. So this is definitely exponential decay. It's the only value we need to look at. Part B says identify the annual percent increase or decrease in the value of the car. So what we need to do is analyze this number, this 0.85, I should say. So I'm going to write this down. 0.85 is the same thing, if you think about this, as 1 minus 0.15, isn't it? You know, think about that. So what we have to look at is this represents in percentage form 100%. The number 1 is the same thing as 100%. 0.15 represents 15%. And 0.85 represents 85%. So it looks like to me if I analyze this situation over here, this helps me understand that there is a decrease of 15% in value for this car. And that's the way you can analyze a decimal, which means a percentage that's less than 1. Let's go down to part C. Estimate the value of when the value of the car will be $8,000. So I need to go back up here and look at that equation. And I'm going to reproduce it here. Okay, so now I want to estimate when this car will be about $8,000. So I think what I'm going to do is I cannot solve that equation. We do not have the ability to solve an equation that is exponential at this point, but we will soon. Let's put this into Desmos. Okay, here we go. Let's put it in here. Y equals 25, which means 25,000, 0.85, which means there's 85% of this vehicle remaining every year, to the X power. Okay, now let's look at this carefully. So I'm going to go back to the presentation. $8,000 is what we're looking at. That is Y. So let's make sure everybody understands that. $8,000 is Y. I'm going to make a note of that. That's the total value of the car. So basically what I'm doing is I'm looking for an ordered pair with a Y coordinate of 8,000. Let's see if I can find that on Desmos. So here we go. Now my graph is going to need to be zoomed way out, except for not. Let's recenter that. Let's rethink this. Let's go back to this presentation. Isn't everything in terms of thousands of dollars, isn't it? So that means that this 8,000 is really the ordered pair 8, because it's in terms of thousands. So now let's go back to Desmos. We don't need to go that far out. I'm going to go ahead and see if I can get in there and estimate that. That's pretty close. I'm going to say it's about 7 for the X coordinate. So I'm thinking that the value of the car will be 7. So let's go ahead and erase this, make this look a little bit nicer. This will be 7, which means that is the number of years that it takes to get to that point. All right. Let's try another one. Okay, in the year 2000, the world population was about 6.09 billion. During the next 13 years, the world population increased by about 1.18% each year. Part A, let's write an exponential growth model giving the population in billions for T years after the year 2000, and then estimate the world population in 2005. Okay, let's go ahead and try it. So we're going to start off with our equation. Okay, this represents the world population. I need the starting amount. Okay. So I'm going to put 6.09. That's my starting amount. The next thing I need to do is represent the growth rate. It increased by about 1.18%. Now let's remember that that is 0.0118 as a decimal. So the way I'm going to represent it is that it will be a growth rate. Oops. As a growth rate. So it's 100% plus it's increasing by 1.18%. And this is in terms of time. Okay, let's remember this though. It's T years after 2000, after the year 2000. So that will be important. So we got the first part of the problem finished. Now let's estimate the world population in 2005. So let's highlight that. Well, how many years has it been? Well, that would be 5 years. So what I will do, because we're going from the year 2000, I'm going to make that a 5. And now we are going to get an estimate to this. So the next thing we do is we get our calculator out. And we try this out. Use your exponent. And I've got about, it doesn't say where to round this, but since we have hundredths in the original problem, I'll use the hundredths. I'm going to say 6.46 billion people. Okay, so there's the first part of this question. Part B, what year will the world population be 7 billion? So what we need to do is look at this, and when we estimate the year, that's Y. Okay? So we want an ordered pair. We need to come up with that. So I think we're going to need to go ahead and turn to Desmos again, graph it, and see if we can determine when that might be. Let's try that out. Kind of forget what that was. And I'm just going to use an X because we have Desmos here, okay? And I'm going to hit the home screen, and this is going to look like a straight line, and that's because we're dealing with such a small increase. Now, if we were to zoom out quite a bit, you can start to see this curve. See that? So it's definitely exponential growth. But that's pretty far zoomed in. So I think what I'm going to do is instead maybe take it to this point. And I'm looking for, what was that? We're looking for a y coordinate of 7. And then we're going to get the year. So let's see here, a y coordinate of 7. We're going to get pretty close here. We're going to get really close. I'm going to say it's about 12. So we're thinking it's about 12. So that means that x equals 12. So let's erase this. Let's put a 12 in here. So what year is that? Well, it's from the year 2005, right? Oops, I'm sorry. It's from the year 2000. It's from the year 2000. So 2000 plus 12 equals the year 2012. So I have to remember those little notes about this. All right, that's today's lesson.